All right, so welcome everybody who's watching on the live stream to this Q+ Hangout. We've got a couple of firsts this time round. The first is that, well, we've changed the way, as you can obviously tell, that we stream the Hangouts. We now have the Hangouts on Air feature. It means that we haven't got quite so many people in the Hangout itself, as usual. So if you need to ask a comment or question during the talk, then please make a comment on the feed underneath the video, and one of us will see it. The other thing is, so this video will be recorded and it should be on YouTube within an hour or two of the talk finishing. The second first we have today is that this is our first experimental quantum information talk. And we're very happy to have Jeff Lundeen from the Institute of National Measurement Standards in Ottawa. It's kind of the Canadian equivalent of NIST, I guess. And he's going to talk to us about some work he's been doing on directly measuring the wave function using weak measurements, which caused a bit of a splash last year. So he's going to tell us about that work and also some follow-up work he's been doing with his group. So over to you, Jeff.
Thank you, Matt. So I work for the National Research Council. So it's a large government laboratory spread out across Canada, and it has a fairly big campus in Ottawa itself, which is the capital of Canada, and in total it has about 4,000 employees. And this work was done in Ottawa at our labs, and it was mostly done by myself and Charles Bamber with the help of 3 undergraduate summer students, so I'll name them: Brandon Sutherland, Corey Stewart, and Abid Patel. And so they were key to building the laboratory from scratch and taking some of the first data for this experiment. And if you have problems seeing this screen share, I've put the slides up on my website, which is www.photonicquantum.info. So first slide, see if this actually works. Oh, something's not working. There we go. Okay, so a little bit of self-aggrandizement, just to let you know that, as Matt said, this made a little bit of a splash. It was a Nature paper, and it was the most viewed or downloaded paper in June of July of 2011. Of course, that doesn't mean read, so all we know is most people downloaded it. And more recently, at the end of the year, the editors of Physics World voted it #2 by a small margin, nearly beat out by #1, which is my colleague from Steinberg, my former supervisor at University of Toronto. So #2 top 10 physics breakthrough of 2011. So this was published in Nature, and then we have a theoretical follow-up that we published in PRL, extending it to mixed states, the idea to mixed states and density matrices, and we're now doing some experimental work demonstrating that, and we're going to show you some of the data from that at the end of the talk. So the wave function was introduced along with the Schrödinger equation, which everybody, I'm sure, in this audience loves quite a bit. Maybe not as much as this lady who got it tattooed on her back. You know, I actually think that's maybe not too bad, but I think this guy went overboard with his tattoo, which I'm not quite sure what equation that is, but it definitely has some size in it, so it's some sort of generalized Schrödinger equation. And the Schrödinger equation, one of the first examples that we learned to use it in was modeling the hydrogen atom. And in particular, we learned that if you take the absolute square of the wave function, that you get the probability of finding the particle at a particular position. But the probability to find the particle at a particular position is not the only thing that you can find from the wave function. In particular, the phase is also important. So if you take the absolute square, you lose the phase. And the phase is equally important for quantum mechanics, as demonstrated by the double slit experiment, where when you send through particles even one at a time through a double slit experiment, they slowly build up this fringe pattern, which is exactly the fringe pattern that you see if you're sending waves through your two slits, waves that have definite phase relationships. The phase is important for for superposition and for entanglement and for quantum computing. It's really at the heart of quantum mechanics, one of the things that's at the heart of quantum mechanics. So if you look at textbooks, and I've read looking for definitions of the wave function in many textbooks, including Shankar and Landau and Lifshitz and Cohen-Tanucci, sort of the classic textbooks on quantum mechanics, and you look at what they say the wave function is, you'll find that often they sort of trick you. They'll say that they're going to tell you what this is later on, but first they need to explain how to use it. But by the time they get to the end of the chapter, you realize that they've never actually explained what it is. They've only told you how to use it. And in fact, that's how we've come to really understand the wave function in terms of the Born rule, which is just telling us how to make probabilistic predictions about experimental results based on the wave function. And that's kind of how we tend to understand that. And that can be looked at historically as an evolution of thought, beginning with Einstein, who said that the wave function does not describe a single system. It relates rather to many systems, to an ensemble of systems. So even that statement, seemingly innocuous, might be a little bit debatable nowadays. And Heisenberg, if you look back, he said of course these people said lots of things about the wave function. I've just picked out particular quotes here. The wave function represents an observer's knowledge of the system. So this seems like a very maybe insightful statement, but also somewhat hard to understand. And of course, Bohr was his usual obtuse self when he said the state function is purely symbolic, which I'm not exactly sure what that means at all. And Merman famously summarized all of these views, which was the Copenhagen interpretation, in terms of a very short and pithy statement, which is shut up and calculate. So that's essentially restating that Born rule definition of the wave function that I talked about. And I'm going to, in this talk, take the opposite slant and say shut up and measure. So I'm not really going to tell you what the wave function means, but I'm going to give you a way of thinking about it, an operational definition in terms of a simple set of operations that we can do in the laboratory to directly measure it. So it gives us a new handle on what the wave function is. And the experimental example that I'm going to be giving in this talk, although the idea is very general, we're going to do an experiment, so we have a specific system, and that system is the transverse wave function of a photon. So you have a beam of photons traveling along, and there's some transverse profile to those photons. That amplitude profile is what we call their transverse wave function. And you can go between position space, which is over here, and momentum space on the right, with a simple lens. So if you go one focal length from the position plane, and then another focal length, that lens performs a Fourier transform to a good approximation. And so you can easily go between position and momentum. So you can consider what's the problem of defining the wave function is that it's very difficult to measure. And the reason why it's difficult to measure is essentially the Heisenberg uncertainty principle, or the Heisenberg uncertainty relation. I'm going to be talking about the relation here. And that relation is that if you measure x, you disturb p. So if we put a pinhole in to see which photons were at a particular position, the light will diffract out and we'll get a fairly even distribution of p. We've completely ruined the momentum distribution on the right. And of course you can scan this pinhole and you can slowly scan out the probability of having the particle at a particular position. But in this type of measurement you don't see the phase. And as I just said, the phase is very important. And in particular, you can't predict the momentum distribution. This is called the 1D phase retrieval problem. And there's some ways around it, but there's no general absolute way of solving this problem. So this talk isn't going to be telling you about the first way to determine the wave function. We've developed good and very effective ways of determining the wave function, but these are sort of reconstruction techniques. And in particular, in the mid-1990s, people introduced this idea of quantum tomography. So in this slide, I'm talking about reconstructing the wave function of a beam of light. And all of these different axes on the left are the in-phase and out-of-phase quadratures of the electric field, which are analogous to x and p of a particle. in a harmonic oscillator potential. And these states are basically plotted in phase space. So this first one on the top left is a vacuum state, and then this is vacuum squeezed. The next one down is a squeeze state, and then we just have different types of squeeze states. And essentially what you want to do is a whole series of measurements on these states, and then find out what state is most compatible with these measurement results. And the easiest way to do that is just to project those states onto different axes. So we know how to do that with homodyne detection, which is essentially mixing that beam of light with a local oscillator, which is a strong laser beam, essentially. And then looking at the difference signal between the outputs of the beam splitter. And that's called homodyne detection. And if you change the phase of that local oscillator, you rotate the axis that you're projecting on, and you get these noise signals in the difference current at these detectors. So these are the difference currents that you would get as you scan through projecting those states on different axes. And then you take those noise signals, and which are essentially sort of like shadowgrams of the state on that axis. And then you can reconstruct these Wigner functions. A Wigner function is just another way of representing the quantum state in phase space. It's completely equivalent to the wave function mathematically anyway. And you can reconstruct these states very well. Of course, you get some artifacts, these little sort of lines coming out from them. That's due to the mathematics involved and the fact that you're not projecting onto an infinite number of axes. But when they first did this, they used something called the inverse radon transformation, which was borrowed from medical tomography, like CAT scans. And it's a very complicated transformation. And nowadays, because that transformation is so complicated, people tend to use something else called the maximum likelihood estimation, where you do a fitting of the data to the most likely state that produced that data. So it's really a reconstruction, and tends to be a very complicated procedure, especially nowadays. So it works really well, but it's fairly indirect, and it would be hard to use this as at least a very simple definition of what the wave function is. So the key is really to go back to, I'm going to go back 2 slides actually, go back to this experiment where you put the pinhole in and you tried to measure X. Now, what's occurred to me many times when I've given this talk is that if I gave this, if I told this to an undergraduate student, a smart undergraduate student who didn't just buy everything their professor said, would say, well, what if you made that measurement of X gentler? What if you just tried to be very careful about it and not disturb the wave function? And in fact, a lot of people just sort of said that's not possible, but in fact it is possible, and that's the whole idea behind weak measurement. We make the interaction that actually induces that measurement weaker, and therefore disturb the wave function less, and so therefore we can make repeated measurements on it and get more information about it. So that's essentially the idea behind our direct measurements. We're going to do a weak measurement of X and then a strong measurement of P, and it turns out that the results of that weak measurement give us the wave function. That's the idea. So if that's all you wanted to hear, you could stop listening to this talk. But weak measurement has been a controversial subject since it was introduced around 1990. And I'm going to go into some of the reasons why it was controversial, and I'm going to try and demystify it. So basically explain it in physical terms so that you can see that it really makes sense. These weird numbers don't appear out of nowhere. And then I'm going to tell you about our actual experiment, and then I'm going to tell you about our extension of the idea to mixed states. So weak measurement, as I said, although its name implies that it may not be as useful or as good as strong measurement because you've just reduced the interaction strength and therefore you're getting less information out of your measurement, it has hidden strengths like this cartoon suggests. And it was introduced in 1988 by Aharonov, which you probably know from the Aharonov-Bohm effect, and Albert and Vaidman. And they've gone on to do many more papers about weak measurement. But it made a splash because it claimed that you could measure the spin of a spin 1/2 particle, and the result of that measurement could be 100. And the way they were measuring it was using weak measurement. So the result of the weak measurement was a spin of 100. So a lot of people said, oh, that's really interesting. I want to understand that. But a lot of other people said, well, if it's giving us such nonsensical results, we shouldn't really call this a measurement at all, and we should just completely ignore this crazy idea by Aharonov and Bateman and Albert. But weak measurements, some people have continued to think about weak measurement, including Paul Kwiat, and it again made a splash in 2008 when Paul Kwiat used it to amplify a very small effect, the spin Hall effect of light. He used weak measurement, this idea that you can make results large, like you can make the spin turn out to be 100, to amplify this very small effect and make it visible using experiments. And this amplification idea has been further developed by John Howell, where he showed that you could make the most sensitive measurements of beam deflection ever using this amplification idea. So I'm not really going to be using this amplification idea. I'm going to be using weak measurement sort of in a more, well, they're using it as a practical tool, a measurement tool, in a way that Aharonov probably never really intended when he said that the spin was 100. But, and I'm going to be going back sort of to the original idea of weak measurement. But I'll show you how that amplification comes about. So to talk about weak measurement, we have to go back to explaining strong measurement. And in particular, there's a model of strong measurement called the von Neumann model of measurement. And in the von Neumann model of measurement, you have your measured system, which is in a superposition of states. So here it's a fuel tank. It's a superposition of different levels of fuel. And then you have your measurement apparatus, which we think of as a dial and a pointer. And the key thing is that the pointer is a quantum mechanical state as well. So it's a sort of two-step measurement. We interact our quantum mechanical measurement apparatus with our quantum mechanical system. That does the measurement and entangles those two systems. And then we measure the pointer, and we find out the results of the measurement. So just to make that a little bit clearer, so here's our pointer, and it's coupled to our system by this spring. You turn on that coupling for a little while, for however long you need to, and you interact that system, and then you measure the pointer, and you find out that the pointer was pointing at a half-full fuel tank, and that collapses your system into a half-full eigenstate. And if you repeat this measurement over and over again, you're just going to find out that the pointer points to an average position, which is just given by the expectation value of whatever operator you're trying to measure, in this case, how full the fuel tank is. In weak measurement, we turn down the coupling between the pointer and the system. So we make that spring much, much weaker. And because of that, we're going to shift the pointer by much less. So the measurement interaction shifts the pointer to the correct value, depending on whatever A is. And because that spring is much weaker, our markings on our meter are going to be much closer together. So that's hard to see on the slide, so I'm going to zoom in. And now you can see that, conversely, if we make our markings the same distance, our pointer is going to be much, much broader relative to them. And in particular, now you can see that even if you shift that pointer by one marking, you're not going to be able to unambiguously say whether the tank was half full or 3/4 full or full. So essentially, weak measurement removes your ability to discriminate on a shot-by-shot basis what the results of the measurement are. So you have this trade-off between information gain and disturbance. And what I mean by disturbance is that because you don't have this information gain, the entanglement between the measurement apparatus and the system is now small. In other words, to a good approximation, or at least as this coupling goes to 0, the system remains in the original superposition that it began in, the superposition of eigenstates. So by itself, this is not very interesting. If you repeated this measurement over and over again, you'd find out that even with weak measurement, the average position of the pointer is still equal to the expectation value that we expect, just psi A psi. So far, weak measurement hasn't really let us do anything. But as I said, the system is left undisturbed. So if you want to make subsequent strong, for instance, or weak measurements on that system, you can. And those subsequent measurements can give you information about the initial state of the system, the initial superposition of the system. Whereas in strong measurement, if you do a subsequent strong measurement, it just tells you about the eigenstate that it collapsed into. And in particular, it can't tell you about the phases between the eigenstates that you started with. So consider if you started off in state psi and you made a strong measurement after your weak measurement that resulted in projecting onto a state phi. So what that'll do is it'll shift on average your pointer to a position which we call the weak value. And the weak value is given by this formula. So this is different than the normal expectation value. This is the average position of the pointer in the subset of systems that were subsequently found in state phi after the weak measurement. So we're doing a weak measurement and then a strong measurement. The strong measurement gave a result of phi. So this is the average position of that pointer. And there are two things you can notice about this formula. One is that the bottom, if the initial and final states are nearly orthogonal, this average can become very, very large. So that's the amplification effect that we talked about. The other thing is that just because of the form of this formula, because it's not Hermitian, maybe it's the right word, it can be complex. And so I'm going to explain what that means. But generally what it means, just to give you a hint so far, is that there's now two components to the weak value, a real part and an imaginary part. The real part gives you the shift of the pointer, which is what you'd expect from the strong measurement. The imaginary part gives you a shift of the conjugate variable of the pointer. So in this case, we're shifting the position, so we expect the imaginary part to show up as a shift of momentum. And I'll show you how that can come about in the next slide. So here I'm going to give you a physical example of how weak measurement can occur. This is an example that's actually was an experiment, the first experiment on weak measurement by Ritchie and Hewlett, in which they demonstrated that spin of 100 effect. So here we're going to use photons instead of electrons, so we're talking about polarization instead of spin. And because photons don't interact with external systems very strongly, we can't use a separate meter. It's not, well, you can, but it's not very easy anyway, particularly at this moment in time. And so instead of using an external meter, we use an internal variable of the photon as our pointer that is uninvolved in the system degree of freedom that we're interested in measuring. So here we're interested in measuring polarization, and we're going to use the transverse position of the photon as our pointer. So we start off with our photon in a Gaussian mode, or wave function, transverse wave function. So here I'm plotting position, and then in the right-hand axis is amplitude. I'm going to follow that along to the right as it propagates through the system. So then we're going to initialize its wave function to a polarization state of 45 degrees with the polarizer. So that's our initial state. And then what Ritchie and Hewlett did is they measured the polarization in the HV basis with a calcite crystal. So this is equivalent to measuring the poly-Z operator. So a calcite crystal lets the V polarization transmit unchanged through the crystal, and it displaces the H polarization. So you get, depending on the thickness of this crystal, you get a controllable amount of separation between the H and V polarized paths. So if this photon was H and this wave function was very narrow, you could tell for certain, because it would be much narrower than the separation between these two paths, you could tell for certain whether it was H or V. In this case, it's a superposition, so there's an amplitude for it to go through each of these paths. And the key thing to making it a weak measurement is to make this separation, 2G, much smaller than the wave function width. So we can't tell on a shot-by-shot basis whether it was H or V. If we had H, an H polarization, and we sent it through and we did it over and over again, then you could tell it was H, because you could build up statistics and find out where that pointer was pointing, and you could find out that it was centered on that upper line. So you can still get good measurement results even if your pointer is much broader than the separation. It's just you have to repeat the experiment over and over again. In this case, we have a superposition. So really the photon is going, there's an amplitude for the photon to go through each of these paths, which I've now described these two transverse pointer profiles, blue and red. So then we do our final, so we've done our weak measurement, And we're not going to read it off yet. Reading it off would be measuring where the photon was in the x direction. Instead, we're going to do our final strong measurement, and then we're going to read off the weak measurement. Because if we read off the weak measurement right away, we'd have to use a camera which would absorb the photon, and that's effectively a strong measurement that we didn't want to perform. So we're going to use another polarizer that's almost orthogonal to the first polarizer. So it's -45 plus some small amount. And now if you look at these two amplitudes, these red and blue amplitudes, you'll find that that post-selection process flips one of them, and it changes the amplitudes by a small amount. It adds plus delta to one, and it subtracts delta from the other. Now if you add those two transverse wave functions together, which you should because you're going to be looking at the sum of the two, the interference between the two, then you find something interesting happens. Basically, for any well-behaved smooth functions, they're going to add up and create another smooth function that is the same as the ones that you started with, but shifted by basically 1 over delta. So there's an interesting interference effect that can happen between these two shifted and flipped Gaussian, say, beams, where when they interfere, you get a very shifted Gaussian. Now keep in mind that most of the light does not get through the system. So it's not like you're moving light from traveling along the axis of the system to very far away. What you really do is you're just selecting out the light that was traveling far away from the axis. But there's two things to notice about this. One is that it gets very large if delta is very small. So if the initial state and final states are almost orthogonal, so that's where you get your spin 100 or polarization of 100 that Harnaff talked about. And the other thing is that if you're trying to measure G, if you're just trying to figure out what that is, then you can make your result amplify that G by a factor 1 over D. So that's the amplification effect that we talked about. So implicit in this measurement scheme, when you say the spin or the polarization is 100, or 1 over delta, there's implicit in that you're still interpreting your result as giving you the value of the property that you're measuring. So in this case, you're measuring what is sigma z, or what is the spin. And although this isn't a standard measurement, you're still interpreting that result as being a standard measurement and interpreting that result in the way you interpret a standard measurement. So that's the controversial part of it. Should we really be interpreting this result as saying the polarization was 100? And a lot of people, there's still a lot of disagreement over that. In fact, there's no real consensus about what weak measurements mean, or weak values mean in general. So that's one of the things that people are still trying to figure out. But in a few cases, they do mean something very clear, and our experiment is one of them. So that's one of the attractions of it. So I mentioned that that the weak value is complex, and I'm just going to give you an example of how that imaginary component can come about. So this is the same experiment, except now instead of post-selecting on an almost orthogonal state, we're post-selecting on a circularly polarized state. So that's a superposition of H and V where you have an I phase before the V. And so once you've done that post-selection, these two pointer distributions, the blue and the red, are going to have different phases, opposite phases, in fact. And because one is slightly higher on one side than the other side, you can see that when you add them together, you're going to have a phase gradient across them. So you're going to have a phase gradient in position space. Now if you take the Fourier transform, go to the far field, or use a Fourier transform lens, and you go to momentum space, you'll know that through the properties of the Fourier transform, if you have a phase gradient, you're going to get a momentum shift, or a shift in Fourier space. And that shift is proportional to the imaginary part of the weak value. There's some constants before it that I won't go into, but that's essentially where that shift comes about. So my main conclusion here is that both the imaginary and the real parts of the weak value are manifest as physical effects in this measurement process. And they can both tell us things about the system. And in particular, our direct measurement experiment is probably one of the first experiments where we've used, where anybody's used both of the components to tell you something about the system. But even in amongst the people who study weak measurement, the imaginary part is often excluded from discussion because there is no analog for the imaginary part in standard measurement. In standard measurement, you only get a position shift of your pointer. You don't get a momentum shift of your pointer. So often people will just say that the weak values equal only to the real part of that. They just exclude the imaginary part. And people have struggled to find out what the imaginary part of the weak value really means in general. And as far as I can see, there is no consensus about what its meaning is. Definitely, it has some very strong connections to fundamental ideas in quantum mechanics, like geometric phase. As you can see, this is a sort of an interferometer, and so there's a geometric phase effect in this interferometer, and it turns out that the imaginary part of the weak value is related to that geometric phase in that interferometer. But that's an aside. In general, people don't really agree on what it means, or whether we should even really pay attention to it. So the message is that weak measurement is interesting because it gives us a new way to investigate quantum systems, but we don't really know what the results of it mean in general. And even worse, the imaginary part is confusing even to the people who study weak measurement. So maybe that's an invitation to try and figure out weak measurement yourself, because we could use some insights, I think. So now I'm going to go on to the actual experimental setup or example that we use in our demonstration. And I'm going to start out with the strong measurement version of what we do. So we don't do a strong measurement, but I'm going to give you what it would look like if we did do a strong measurement. There we'd start off with a beam of light, and it has, so I should back up a second. We're going to flip the role of the polarization and transverse wave function in that Ritchie and Hewlett example I gave a couple slides ago. So now the pointer is the polarization, and the thing we're measuring is the transverse wave function, which will no longer just be a Gaussian. It can be whatever we want. So we start off with a polarization polarized in the vertical direction. A beam of photons coming out of a fiber is how we do it. And then we initialize them to some wave function that we want to measure. So we need to know this wave function to some degree, or else we won't know we've measured it, properly. And the way we measure position is we use a small sliver of half-wave plate, so it only covers a small area, and the actual thing we're measuring is a projector of x. So we measure whether the photons were at this position or not. If this wave plate rotated the polarization by 90 degrees, then we could tell for sure by measuring the polarization at the end of the experiment whether the photon passed through that position or not. So if the photon was passed around it, it would end up at the vertical detector because its polarization was unchanged. And if the photon passed through the wave plate, it would be rotated completely orthogonally, so it would always go to the orthogonal detector, so we can perfectly discriminate whether the photon was at x. And if we scanned our wave plate, we'd find out that the average number of clicks at the orthogonal detector would give us the probability of finding the photon at x, the absolute squared of the wave function. So that's a strong measurement. So now we're going to do a weak measurement, and to do a weak measurement, our pointer is now the polarization, and so we're going to rotate the polarization by much, much less than 90 degrees. So now, if a photon travels through that wave plate, it only gets rotated a little bit. And it might go to the detector that told us the photon was at x, but it might also go to the detector that told us the photon was not at x. There's some error in our measurement now. It's not unambiguous. So from a single run in a weak measurement, we get little information. And what really you should think about this experiment, the way you should really think about what's happening is not as billiard balls going through the experiment as I've drawn, but really as amplitudes. And so at every point we have this sort of odd spatial polarization beam where the polarization is rotated by just a little bit at one point. And then when you focus and send the light to our detectors, you're going to get interference between all those different polarizations. But if you measure the average rotation of all of that light, so looking at the difference between 45 and minus 45, again, even with a weak measurement, as you scan that half wave plate across, you're going to map out the probability distribution of the photons, the absolute square root of the wave function. So this is just telling you that without any post-selection, a weak measurement gives you the same thing as a strong measurement. The average rotation of the pointer, or of the polarization in this case, is just going to give you the probability distribution. And just like in the last example, the conjugate variable of the pointer held the imaginary part of the weak value. In this case, the conjugate variable of the pointer is the circular polarization. So we're looking at an imbalance between the left-hand and right-hand circular polarizations to give us the imaginary part. And in this case, because the expectation value of A, or a position, doesn't have any imaginary component, the imaginary part will be 0. The average rotation in that basis is 0. But once again, you can consider what happens if you subsequently do a strong measurement. Our weak measurement is now only disturbing the wave function a very small amount, and so our subsequent strong measurements can tell us about that initial wave function. And our subsequent strong measurement will be a strong measurement of P. So we take our Fourier transform lens, and we go into the Fourier plane, and then we just put a pinhole there. And so we select only a particular value of the transverse momentum. So we're going to do a weak measurement of the X projector, and then we're going to do a strong measurement of P. So what does the math tell us? Well, the math is really simple. We take this weak value formula, which I haven't derived for you, but it's fairly simple to derive, but I don't really want to put that in a talk. But so we take as our operator A projector of X. Our initial state is the wave function that we're going to determine, and our final state is a momentum eigenstate. You sub that in, and you get this formula for the weak value. And the thing on the right on the top is just the overlap of P and X. If you set P equals 0, then that just equals 1. And the thing on the bottom is just one component of the Fourier transform of the wave function, which, if you set P equals 0, is also a constant. So all we're left with is two constants times the thing on the right, and that's just a projection of X onto psi, which is just the wave function. So the weak value is just proportional to the wave function. So in this case, the real and imaginary parts of the weak value have very clear meaning, They are the real and imaginary parts of the wave function up to a proportionality constant. Now, of course, every measurement is going to have a proportionality constant in there, in fact, because you have to calibrate your system. You have to calibrate those markings on the meter. So that proportionality constant is a little bit of a red herring. It doesn't even really need to be there because every measurement is going to have one. As I said, it just has to do with the calibration of your system. And in fact, you sort of can self-calibrate your system because we know the wave function is normalized. So if you normalize this over all x, then that k will just drop out. So this is a good way of measuring the wave function. And I call it direct because we get these two rotations on our pointer that we can directly read off without any sort of mathematical trickery or reconstructions. And those two rotations just give us the real and imaginary parts of the wave function. So as you can see, it's a lot more direct than tomography generally is. And was there something else I was going to say there? I can't remember what. Okay. So this is what our experiment looks like as a schematic, of course. So we start off with our linear polarization. We have our half wave plate. We rotate the polarization to 20 degrees. Then we end up with this weird polarization state on one side. We go to the Fourier transform. We get interference between those various polarizations. And then we post-select on p equals 0. So we just put a pinhole on axis. We look at the difference between the left-hand and right-hand circular polarizations. So that gives us the imaginary part of the wave function up to a proportionality constant. And we look at the difference between the 45 and minus 45 degree polarizations. And that gives us the real part of the wave function up to a constant. So now I'm going to tell you about the sort of more technical details of the experiment. This is when we were building our lab. This is Corey Stewart. So I'm next on the left. So going from right to left, Corey Stewart, me, Abid Patel, Rick Gerson, our technician who helped, and this is Charles Bamber, who was another research officer heavily involved in this project. How do we produce our photons? Well, we take a strong pump pulse and we send it through a nonlinear crystal through a process called spontaneous parametric down conversion. occasionally one of those strong pump photons splits into two down-converted photons with half the energy. In this case, they're orthogonally polarized. Then we split them up on a polarizing beam splitter. And these photon pairs are produced always in pairs, but only very occasionally. So if we get a click at this detector, which we call our heralding detector, then the other beam, which is going off to the bottom right, will necessarily have a single photon in it. We call this a heralded single photon source. And that's how we produce our photons. This is our requisite experimental setup picture. I actually don't show the whole weak measurement setup. This is more how we produce the photons. So we have a TISAF laser on the right. We convert the light to blue. Then on the left, we have a TISAF laser. We convert the light to blue. Then it goes over to the right side of the table. We convert back to red in the down conversion process. So now we have two orthogonally polarized photons. One of those photons goes off to a multimode fiber, which goes off to our heralding detector. And the other photon we send into a single mode fiber. So sending the photon into a single mode fiber is our way of initializing the wave function. We're basically filtering out all those photons that didn't have a nice wave function that matched the mode of the fiber. The mode of since the fiber is single mode, only those photons that match that mode, which is essentially a Gaussian, get transmitted through the fiber. And then down here we have our polarizer, and then where this piece of cardboard is, we have our collimating lens. So that makes the photons travel down the table as a collimated wavefront. And this piece of cardboard actually masks off the lens in the vertical direction because we want to do the easiest experiment we can. So we want to do a one-dimensional experiment. So we mask it off so it's only a few millimeters high in the vertical dimension. And then our wave plate we scan across in the horizontal direction on this motor. Down off the screen at the top is our 1 meter focal length for a transform lens, and then even further up is our pinhole and our readout of our weak measurement. So what do we see? So start off, I'm just going to say firstly that the picture on the right is looking at what I just talked about from the opposite direction. So now at the top is the first polarizer in our setup. So right behind that is the fiber. Then the light goes through this polarizer, and then it gets collimated by this lens. We've removed the mask so you can see everything, but there should be a mask in front of here. And then this thing at the bottom is our wave plate sliver that we cut with a diamond saw, and it's about 1 millimeter in width. So as we scanned that through, we looked at these two rotations in the circular and 45 minus 45 basis, giving us the real and imaginary parts of the wave function. And we saw the two curves that you see at the top. So I should say that the wave function that we were hoping to measure is the Gaussian wave function that's emerging from the fiber. We then collimate it, so it has supposed to have a flat wave front or a flat phase all the way across it. Unfortunately, we couldn't buy a good enough lens that was big enough to capture all the photons. So again, we're modifying the wave function by truncating it. So what we expect to see is a truncated Gaussian with a flat phase. And we were very confused for quite a while because we weren't getting this flat phase that we were expecting. And this lens we bought it to be a very good lens. It was specified to be a lambda over 100 in terms of its performance. It turned out that the resolution of this was due to the fact that Thorlabs basically didn't have the right specifications up online for this lens. So the design performance of the lens is lambda over 100, but the actual performance of the lens, as it's fabricated, is lambda over 4. So the lambda over 4 sort of explains this variation in phase, or the variation in the real and imaginary parts as you go across the beam. And in fact, we verified that these are consistent with doing a wavefront measurement of the lens using a zygo, which is sort of how you professionally do this type of measurement of profiles of lenses and mirrors and things. But the key thing is that even though we had this odd phase across our wave function, when you take the real and imaginary part and you calculate the wave function absolute squared, you see this truncated Gaussian, just like we expect. So this was pretty encouraging. And suggested that we should go on and try different wave functions. So it's not all that easy to modify the wave function in a controllable way where you know what to expect. We used a reverse bullseye filter, so that transmits more photons in the middle than at the edges. So that meant that we're no longer truncating our beam. And so what we did was we did the same measurements as before, and we calculated the absolute value of the wave function squared, and then what we did is we took a detector and when we scanned it right across the lens where we were supposed to be measuring the wave function, and directly measured the probability distribution of the photons. And those are the blue and the red curves, and you can see they agree pretty well. So the bottom axis is position, and the vertical axis is the probability density. But of course, it's the phase that really tells you whether we're doing this well or not. So our first way of measuring the phase in a crude way, or testing whether this does measure the phase in a crude way, was putting a piece of glass across half of the beam. So half of the photons are going to travel through this glass and pick up a large phase shift, or a phase shift of some type. And we actually don't know what that phase shift is. It's hard to measure. And you can see that in our real and imaginary parts, we see this discontinuity in the phase, right in the middle. But even though you have this discontinuity, when you take the absolute squared of these real and imaginary parts and add them together to get the absolute squared of the wave function, you see we get the wave function just as before, except for this little point here, which we attribute to diffraction from the edge of the glass. So we're actually losing photons there. So we actually, even though the glass should transmit all the photons, we're going to lose some at the edge due to them scattering off of that. So it seems like it's working well. Let's try out some more difficult wave functions. Let's tilt it. Let's tilt the wave function. So now a tilt is equivalent to a phase gradient across the wave function. So we tried a bunch of different tilts. We tilted it by 10 microradians per step. And as you can see, starting off on one side with a large tilt, you get a couple fringes, and then you get less fringes, and then you get more fringes. But it's a little bit messy because we already started off with this weird phase profile due to that imperfections in that first lens. But you can subtract out that initial phase, and when you do, you see that, as you expect, you are getting these flat phase profiles just due to a simple tilt that changed by exactly the right amount. So here on the bottom right, we have the phase gradient on the vertical axis and the beam tilt on the horizontal axis, and each of these points correspond to one of these graphs from left to right, the slope of these graphs. And you can see that they agree well with theory. And then we tried putting on a quadratic phase on the beam. And again, we did that by just moving the lens in and out. And again, you can see it agrees well with theory. So it seems like this works. One last thing that we tried is, as I said, when you do no post-selection, so that means no slit afterwards, the same measurements that you're doing for the weak value should give you the standard expectation value, the probability distribution. So we opened up the slit, and as expected, we saw the imaginary part of the wave function, or the imaginary part of the weak value, I should say, go to 0. These are these blue points. And the green part basically traced out the probability distribution. Red is from a direct measurement, just scanning a detector across the lens. So it seems to agree well with what we expected. So that tells you how to do it in terms of X and P. What if you wanted to generalize this to any quantum system? Well, the key thing is to identify two mutually unbiased bases. If you do that, then those play the role of X and P. And a mutually unbiased basis is just two bases where the eigenvectors in those bases have the same overlap no matter which pair of eigenvectors you pick. In particular, you can pick one state from that second basis that you're going to do a strong measurement in, and any state in the first basis, which you're going to measure the wave function in, or quantum state in, this basis A, and the overlap between any A state and this particular B state will not only be constant as 1 over n, but be phase-free. So the phase won't change either. That plays the role of P equals 0. This is really a convention. You can actually pick any state you want in that second basis. It actually sets the reference frame for your system. But you're guaranteed that there is at least one state. And then if you go through the math, you find out that as you do a weak measurement in the A basis of that projector and then a post-selection on the B basis, the average result of that weak measurement will just be the amplitude in front of that A vector in the superposition that you started with. So I'm not going to say too much more about that. And in fact, it turned out that we had already done an experiment, unbeknownst to us. Myself and Ephraim Steinberg, who's my former supervisor at University of Toronto, had already done an experiment where we had actually measured the wave function of an entangled particle pair. So we had done a measurement in Hardy's paradox where we had a photon pair, one photon in each of two Mach-Senders, and they interact in such a way that they get entangled. And it turned out that we were doing weak measurements to try and find out where those photons were in a particularly paradoxical case where they ended up at these two detectors. So I won't go into it too much, but the key thing is that we have these two Mach-Sender interferometers. We're doing a post-selection on these two detectors, D plus and D minus. So that's sort of doing a wave-like measurement. And then we did weak measurements inside the arms of the interferometers, so in the inner arms and outer arms. So that's like doing a which path measurement. So these are complementary bases, and they are appropriate for doing this measurement of the wave function. So we measured in which pair of arms the photon pair was, while post-selecting on this wave-like behavior, which is them ending up at this particular pair of detectors after this beam splitter. So in those cases, we expect the theoretical quantum state to look like this, where the red text is. This is the state that we're looking at, where the first photon is in the inner and the second photon is in the outer arm of the second Mach-Sender. And then what we do is we scan through each pair of arms with our weak measurement. I'm not going to tell you how we did it, and this is what we got. So we didn't do a very good job, but you can see where we saw one, we got a positive number that was fairly large. And in particular, where we wanted a -1, we got a minus number that was pretty large. So this works for entangled pairs of particles as well, basically. Although I expect that somebody could do a better experiment than we did if they were trying to get the actual wave function. So I don't have much or any time left. How much time left do I have, Matt? Should I stop or? Oh, I can't hear you actually. Still can't hear you, but I'll put up your hand. Tell me how many minutes.
You can have a few more minutes.
A few more minutes, okay. So I'm going to go through this section fairly quickly, but essentially I'm going to tell you about what happens when you generalize this to mixed states. So first question is, what do you see if you send through a mixed state through the original experiment? And the answer is that you can't tell you had a mixed state. If you just did those measurements I told you about, there's no signature of having a mixed state, no clear signature at least. So you really have to do an extension. And one way of thinking about this extension is not just doing a measurement of x in a particular p, but scanning both x and p. So you can either do two weak measurements of x and p and then look at the result of that joint weak measurement, or you can do a weak measurement of x and a strong measurement of p, but measure all p, not just p equals 0. And it turns out that the thing that you get as a result of that joint measurement of x and p is this complex number, because we expect the weak value to be complex. And it's equal to this very simple distribution. So you take your density matrix, and on the left-hand side, you project onto a p state, and on the x side, you project onto an x state. And then you have this phase term right here. So this turns out to be a pretty interesting distribution. You can prove that it completely determines the density matrix. Hold on one second. I'm busy. Oh, sorry. Oh, the fun of having these online talks. Okay, so yeah, so you can prove that this thing you measure as you scan x and p completely determines the density matrix. So it's sort of like the Wigner function. It's equivalent to the density matrix. Now, unlike the Wigner function, it's complex. So it's not as good as the Wigner function in the sense that it's not always real. But on the other hand, the Wigner function is supposed to be a probability distribution, but it goes negative. So it's also not a very good probability distribution. Arguably, this thing that we're measuring is a quasi-probability distribution that is complex, so it might be said to be worse than a Wigner function. Another thing that makes it worse than a Wigner function is that a Wigner function, you can rotate it, and you'll get the right marginals for any axis that's a combination of x and p. You can't do this for this quasi-probability distribution that we measure. And here I just plot for an example of Fock state, and this is what the real and imaginary parts of this quasi-probability distribution that we'd measure is. This is what's in that physical review letters that I talked about. But like the Wigner function, its marginals are equal to the x and p probability distributions, and you can find out the expectation value of any observable c by a simple overlap. So it has a lot of properties in common with the Wigner function and other quasi-probability distributions. So when I calculated this, I asked, what is this quasi-probability distribution? Has anybody else looked at it? And I slowly, it took me a long time, found people who had looked at it before. And in particular, Dirac had derived it when he tried to come up with an analogy between classical and quantum mechanics. So he derived it for general operators. So I thought, well, maybe I should call this the Dirac distribution. But then when I read more about it, I realized that this guy Kirkwood had actually looked at it not for operators but for states back in 1933. So some people call it the Kirkwood distribution. Maybe we should call it the Kirkwood-Dirac. But in electrical engineering, there's this guy Rehacek, and in electrical engineering, it's known as the Rehacek distribution. So maybe I should call it the Kirkwood-Dirac-Rehacek distribution. But then I started coming up with more and more articles that claim to be the first to introduce this, including Wolf and Walther in electromagnetism and atom electric field interactions, Meta, Martineau Hill, some pretty famous people. So in the end, I'm not quite sure what to call it. Dirac distribution has a nice alliteration, so maybe I'll stick with that. But anyway, it's been studied, and a lot of people think it has some benefits over the Wigner function, and it's actually quite widely used in electrical engineering for signal analysis. So we've actually done some preliminary measurements to measure it. It's a very similar experiment to what I said before. You have your weak measurement using the wave plate. Now, instead of having a pinhole, we have a camera. So we're post-selecting all the different momentum simultaneously. In front of that camera, we still have to measure the different polarization components. So we put a polarizer at 45 minus 45, and right-hand circular and left-hand circular. And essentially what we're doing is we're making a joint measurement of x and p, and this gives us the Dirac distribution. And this is what we see. So these are our preliminary results. Here is the pixel on the camera, which is momentum, and then this is us scanning the x position. And these fringes are essentially the phase of the wave function. So this is for the same truncated wave function that we did before, and you can see that truncation on the edges here. But what's really going to be interesting is when we start doing this for true mixed states. So that's our next challenge. And then also we've published some papers showing that this might be useful for laser beam characterization, for characterizing the wavefront, which is sort of the classical analog of the experiment that we did. And I've also been in discussion with other people at NRC who've did some pioneering work on measuring the wave functions in small molecules using out-of-second pulses. This is Paul Corkum, getting the Order of Canada. Paul Corkum was an NRC researcher. He's now at the University of Ottawa, and this is our Prime Minister. And so that ends the talk, almost on time. So to conclude, the idea behind the direct wave function measurement is universal. It not only applies to the transverse wave function of the photon, but also could be used for frequency time measurements, or measuring the electron spin state, or as I showed, entangled multi-particle pairs. And if you want to use this as an operational definition of the wave function, you'd say that the quantum state is the average result of a weak measurement of a variable, followed by a strong measurement of the complementary variable. So that's a very pithy definition, operational definition of what the wave function means. And I'll just end with this quote from a student of Willis Lamb's, where he was recounting a story where Willis Lamb was at Columbia writing the Schrödinger equation on the board, and he got up to Psi and he said, "Don't worry about what this means, you'll get used to it." That's it. Thank you. Oh, I still can't hear you, Matt. Okay, now I can.
Okay, thanks very much for that, Jeff. Can you hear me now?
Yeah.
Oh, okay. Thanks a lot for that. So I guess what we'll do now is I can invite other people into the Hangout to ask questions. So if anybody does have a question, just write a comment underneath the video feed, and I'll invite you into the Hangout to ask that. while we're waiting for that, maybe I'll ask a question to start. So one thing I was wondering about, this is maybe more of a theorist's question, is at the beginning of the talk you mentioned other kinds of state reconstruction methods. So I was wondering, how does this perform as a state reconstruction method in terms of efficiency? I imagine you have to use an awful lot of copies to get the weak measurements. So, you know, how are you doing in terms of accuracy per copy compared to other methods of state reconstruction? Okay, so I doubt this is doing as well as tomography in terms of signal to noise. And I haven't actually solved this because it's a difficult question, and I'm not a theorist. But even in tomography, signal to noise is a difficult question, partly because you use these convex optimization techniques, and it's hard to figure out how errors propagate through those. So you can make assumptions like you have the optimal error. You meet the Cromera-Rao bound or something like that. I very much doubt this will meet the Cromera-Rao bound because you have this limit that you're taking where you can make the experiment as weak as possible, and you don't really get any benefit in terms of signal to noise by making the measurement weaker. So you have this free variable that you can change that definitely makes the signal to noise worse, and there's no real way to set it arbitrarily. So the short answer is I haven't figured it out. I doubt when you consider signal to noise that it'll do better than tomography. So if that's your concern, you should probably do tomography. But where this does benefit you is that tomography requires that you have very good control over your system in the sense that you have to be able to manipulate it to do these measurements in many different bases. So in this case, you really only need to access these two bases. And that can be a lot more convenient for people in various systems where we don't have as much control. So it has a sort of qualitative difference from tomography and a practical note. So and a good example of this is we were the first ones to measure the quantum state of the transverse wave function of a photon. And other people have tried to do that before unsuccessfully because it's actually somewhat difficult because you have to do all these different measurements. Okay, thanks. Do you have a question, Daniel? I don't see anybody on the feed asking. No questions on the stream. Okay, so I don't know how well this system of broadcasting the seminar has worked. So if there aren't any more questions, I guess that's it. And we should say thanks to Jeff again. If there's anyone out there, I thank you for watching. Yes, the video of this will be available within a few hours, so hopefully more people will watch it on that. The slides are available on my website at www.photonicquantum.info. Okay, so thanks a lot. That's it, I guess.